right, most of the audience are technical, so if I believe, and tell me if I'm wrong, you all understand what the MO is. So if you got any technical at some stage, let me know, but I try to stay on the technical side and I try to show what we've done, and we've done a lot, so I try only to summarize the main outcome. I can't see the chat, so if you got any chat, let me know a question or stop me. So I'm going to present what the ATMAC project is. The objective was DPI so former DAF, Department of Primary Industry. And then we manufacture LVL, we manufacture glulam, and the nice part of this project, actually, we got positive commercial outcome of this project. So and I'm going to talk about that. So what's the ATMAC to project structures? It's a project was awarded by the Agricultural Trade and Market Access Corporation to Forest and FWPA, and it was in partnership with the Green Triangle. And the aim was to try to find high-value market for logs that usually used for pulpwood or wood chips, and try to get enjoying wood products out of those logs. And there was economic outcome, which was done by Team Woods, Industry Edge, and DPI was doing the technical component of the project. All the idea started when China stopped importing pulpwood in 2020. Now they start importing it again, but the idea was ATMAC gave some money on the table for people to try to find alternative market for what China stopped importing. And so the project looked at two different types of wood. One was hardwood, which was hardwood blue gum, so southern blue gum or Eucalyptus globulus. So basically those logs, they are grown for volume, they are grown fast, and they are dominate the hardwood resources in the Green Triangle. So they're very grown for pulpwood. There's no thinning, nothing. They just grow, harvest, and chip the woods. And the second was Rayatapang, which the species is grown for sawn timber, but they got some first and second thinnings, small diameter logs. They got a less value market, so can we use those? And some of them are exported for pulpwood, so can we use some resources, high value market for those two resources? So southern blue gum or globulus and thin first and second thinning for Rayatapang. And the steering committee decided to look at two different structural products. The first one was LVL or laminated vernier lumbers. I think you all know what LVL is. Put in the chat if you do not, but I believe you all know. So the first one was laminated vernier lumber, and the second one was glulam. So we're trying to look at what can we manufacture those two products from the resource of interest. So DAF objective or DPI was first literature review. Then we need to look at get some trees, look at the characteristic of the resource. Then we need to assist and do some full-scale production trials. And then we need to test the manufacture of the products and test them. All right. So log harvesting, we went to the Green Triangle in 2023. We went to harvest some blue gum logs on the left and Rayatapang on the right. You can see my colleague Thomas here was looking for koalas because you cannot harvest a tree if there's a koala in there. Actually, my neck was sore after that. So we harvest 120 blue gum logs and 60 Rayatapang. And while we target different two plantations for the blue gums, 15 years old and 19 years old. And for the Rayata, we look at first thinnings, 11 years old, and second thinnings, 18 years old. So all the diameter we targeted were average diameter or relevant diameter for the project where they have a large volume of them. All right, the log were shipped to Brisbane for processing. This is the Salisbury Research Facility in Brisbane. And then when we had the tree, so the first part was manufacturing LVL. So we start by peeling to manufacturing the LVL. So we got the logs, we cut them into billets, and then we peel them. So if you haven't seen that at the The log is on the right. It's called a spindleless, and you can see the veneer coming on the left. Yeah, so there used to be a log. To me, peeling is like, you know, when you got a toilet paper roll. It's basically the same. You peel the trees into veneers. So we've done that. We peeled 2/3 of the logs. We managed to get like 3 kilometers of veneer at the end. So you can see a little bit on the right how much we peeled quite a lot. One of the biggest dry at the Salisbury Research Facility. And then we look at the veneer. We characterize the veneers for visual grading, MOE distribution, and also recovery, just to make sure that when we peel them, we've got enough veneers to manufacture LVL. So interestingly, in terms of visual grading, we mainly have D grade. So A grade is the nice top visual appearance veneers. D grade, you can't use that for visual products. That's for most of the veneer were D grades. A few failed as well, and it was the same for Tapang. We have only had D grade veneer or veneer that we couldn't use for in the manufacturing. So the result of that is that you cannot make appearance LVL. It cannot be manufactured. You're always going to get a product that doesn't look nice. It doesn't mean that it doesn't perform, but in terms of appearance, you're not going to get, you won't be able to do that, or unless you buy nice veneer from another source and you put them on the face. But however, if you're looking at the MOE distribution, if you know MOE for the 15-year-old blue gum, the average MOE of the veneer was 15,000 MPa. For the 19-year-old side, it was 20,000 MPa. This is high. This is very, very high. So despite being a resource which is grown for volume, it still produces veneer of very, very high MOE values. MGP10 NGP10 is half of what we get on average for the blue gums. For the Atapang, we had between on average between 8,000 to 10,000 MPa. So just a bit of distribution, MOE distribution. If you look on the right-hand side, this is some MOE distribution for the 19-year-old site, and you can see that at 50% of the veneers got a MOE higher than 20,000, and we can even go up to 30,000 for the top veneers. For the younger side is a bit less, but still we can recover a lot of veneer with very high MOE. And for the that should be a right Tapang. For the right Tapang, we've got of course the MOE is less, but we still got, like for instance for the T2, still 50% of veneers got an MOE higher than MGP10. So we can still recover some high quality veneer with high mechanical properties. And if you're looking at the recovery, it's basically similar to the current industry recovery, which means that when we peel, we're not going to reject more veneers that was actually currently encountered in industry. So recovery is good. It's matching what the industry sees. So it can be used. Point is, the resource can be used for manufacturing LVL. So we've done some numerical simulation just to understand which type of LVL and which proportion they could be manufactured. And we try to look at different scenarios. We either manufacture 100% blue gum LVL or hybrid LVL, which is using both Ratapang and blue gum veneers. And we try to either do some LVL 15 to LVL 21, so it's very high. So the 15 and 21, they are the MOE value. So LVL 15 and 21, they are very high value products. So they're very high performing products. And that's what the market analysis shows, that there is a niche market for very high performing value to replace steel in houses. And LVL 12, which is very similar to MGP 12, which is going to be a commodity product. So we're trying to see if we can remanufacture commodity products and as well very high performing products from the resource. And that's the interesting part. So if we're looking at, if you're only doing blue gum veneers, we could, for instance, manufacturers use 80% of the volume of the veneers to manufacture LVL18. And then we were just going to get 20% we're going to use in the low performing products. However, we could use 100% at the bottom, 100% of veneers to manufacture LVL15. So we can use all of veneers. We know we're going to get LVL15. So high performing products. And then if we want to go to even higher performing products, we can use 40% of our volume to manufacture LVL21. And the remaining of the volume, with 58%, we can manufacture LVL12. So the idea with this simulation, a manufacturer could basically have two different products, one commodity product, but we still have enough volume to manufacture one of the high performing products. And if we look at hybrid, it's the same. It's we do alternate veneers between blue gum and royal tapang. And we can do the same if we can use 23% of LVL18 and 64% of LVL12, or we could also manufacture 63% here of LVL15. So but if we're using all of them, 100% of the veneer can be used to manufacture LVL12. So there is a high potential to manufacture high performing products or commodity products with the veneers, and that's quite a big outcome for the project. Is that yes, you can manufacture from commodity to high value products with those resources. Then we went on manufacture the LVL. This is a team at Salisbury manufacturing some LVL in our semi-commercial facilities. We did 5 different type of LVL. So first one, it was one scenario where we can manufacture LVL12 and LVL21. Another scenario when we could do an hybrid where we can manufacture LVL12 and 18. Another one we're just trying to do 15 as an hybrid products. So we manufacture those scenarios. We test them in bending, shear, and compression. And when we've done, this is at the top, this is our results. And at the bottom, these are some LVL that you can commercially buy. So if you're looking at more the commodity, which is LVL12 and LVL15, which is a bit at the border, it does either equal or is performing better than the commercial products. So we can manufacture products that can directly compete with the commercial products, commercial LVL. If we're looking at the high-performing LVL, you cannot find some on the market. So we compare them to the F20 and F34 sawn timber. And once again, they are performing as well or better as the very high-performing sawn timber. So if you want to get you can't find F34 sawn timber, you could actually replace it with one of the high-performing LVL. So yeah, that's how it comes. So and we also check that we can glue it, and then you can glue the LVL, so you can pass all the durability bond between the veneers. So we know to glue it, we can manufacture high-performing LVL. So in summary, basically, the resources they offer you can manufacture high performance LVL and a little bit of commodity, or you can do a lot of commodity if you do hybrid, but you can still get a lower volume of high performing LVL. So it's you can have different strategy, but you can get basically good LVL products if you want in one way, but you just can't get visual appearance products. And we can glue the veneers. It's not an issue, just a little bit of trick on the glue on the manufacturing process. And all those products, they are as good or better than commercial products. So it could be manufacturers. And so it's a no-brainer. It can be done. We've done the basic research for that. It can be done. The issue with LVL is that you got only one company who is doing it in Australia, and they got their own resource, And so hopefully you got another one who's going to start soon in Victoria, but not a continuous process. But there is we can pin Australia, which just still do not have the capacity to manufacture the product yet. So so they will come. So but that basically study shows that the resource will work for that. So if we move to glulam now, from sewing to glulam, so we saw some one side of the logs were sewn into board. You can see some of the board on the right hand side. So I think that's the video. So just the so at the Salisbury Research Facility where we transform the log into planks, into boards on the right hand side. We've got about more than 1,000 boards. We dry them, either kiln dried or hair dried, to get the final boards. And then we took 360 board. We dress them, we plant them, and we characterize them for MOE, density, mechanical property, and grading. We grade them as well according to the Australian standards. We measure the imperfection before and after planning. The issue with globulus, it's a species that can twist a lot, you can curve a lot, so it doesn't stay straight when you dry. So we try to characterize the imperfections just to give a bit of information to the industry. We also look a lot of different characteristics in the Australian standards. I'm not going to spend too much time on that, but just still to give information of the industry of what the resource looks like. Then we test the board in tension, shear, compression. Measure MOE density, and some of the results just to quickly show, but this is a tension for the southern blue gum, and you can see a very large, this is the MOE on the right hand side, a very large variability in the results. You can go up to 20 MPa in tension, up to 140 MPa. And it's mainly due to the knots and other defects. If you look in for ATMAC, it's the same. You've got some boards that actually they couldn't even take the load, the minimum load the machine was applying, but it doesn't take a lot of tension for the ATMAC. But you can still try to fit some equation, and I don't spend too much time on that. But you can start predict the strengths to the measure based on different equations that we developed. You can do the same for tension. Tension, same, a lot of variability in tension, and we can go up to 70 MPa. And the ATMAC, it's also very low in tension, but and same thing, you can do some equations. I won't spend too much time on that. I should have a slide actually. So if you look at the MOE distribution for the blue gum, again, you've got about 50% of the boards got a MOE greater than 15,000 MPa. ATMAC is it's a bit lower. 50% of the board got a MOE greater than 600 MPa, so it's pretty low. But you can still get some board with very high MOE, greater, like about 20% of the board got a MOE for greater than 20,000 MPa. So very high MOE. You can really recover very high density, very high stiffness boards. Again, we did some numerical simulation to understand which type of glulam we could get and in which volumes. We estimate the MOE, the bending strain and shear strain with different level of confidence in the results. And the market analysis show basically what we need. We need GL18 and GL13 in the Australian standards. So GL18 is high performing products. GL13 is more commodity products. And so if you look, so for instance, different scenario, if you try to do only one southern blue gum glulam, you should be able to get about a GL17, GL18, maybe GL13 in bending strength, but we're not very confident with that value. So we're going to get about GL17, 18 just by only doing one blue gum products. If we try to do two different products, 40% of the board could be used to do a GL18 and 60% to do a GL13. So you can still use your board in different ways to be able to do two different products. If you try to do an hybrid products, you could also get a GL10 and a GL18. And again, hybrid products, you could get two GL13, which is one is purely blue gum, one is hybrid. So there is a way to mix your board to get also this kind of commodity products and high performing product. We did some gluing trial. We glue the we try to glue the board for durability. We use different type of glue, and we found that the high density board, which is greater than 850 850 kilogram per cubic meter, were very hard to glue. And we found that if you put them through a planer first and you sand this board after, we actually managed to get satisfactory bonds. But we know that when it goes to a commercial try, you need to be careful how you glue those high density boards. It's about 20% of the boards. We did some finger joint as well. We have a bit of issue finger jointing the boards, but also it's because we were not very well set up for that. So still need a bit more work in this area, but it didn't work very well. But I think it's more us than the resource. All right, so we went to WTI, which is a wonderful timber industry in Victoria. We brought them the boards and we asked them to manufacture glue them for us. And we manufacture 4 Southern blue gum boards and 3 hybrids. So the board is on the right. This is some of the manufacturing in WTI. This is the grading, the finger jointing, and the board in the press. And this is a team of WTI with the manufacturer beam. And they really loved it, and I will talk to that about it later. So they were fantastic. They were so helpful. And so what they found, they say that the things they can produce these products in the commercial facilities. We had a bit of issue with finger jointing, but it was because we have very thin boards. So they don't see there should be an issue when a thicker board will be delivered. So they don't find that an issue. The thing that the resource is very well suited for manufacturing GLT because there is no structural market. It cannot be used for framing. If you got a defect, it's easy. You cut the defect, you finger joint the board. So you could actually, what they're calling, upgrade the board by removing all the defect and getting a higher performing boards. The fact that even if you got a lot of imperfection in the boards, you got a lot of cupping, bow, they say, well, if you manage to sew it a little bit bigger and not have we can plan the board first, remove all the imperfection, do our grading, finger joint, and then manufacturing the GLT. So just one additional step to get rid of the imperfection, but they don't see it as an issue. They don't really like the hybrid board. We've got both the Ratapang and blue gum, and they love it so much that they went to apply for another grant to get that manufactured. And the last news I've got, and probably in a couple of weeks, they may actually get the first one on the market. So that was the outcome of the project. They love the project so much that they actually get a partnership with a mill to be able to sew those boards to the dimensions they want and manufacturing those boards. And they love it because they can access this resource at a lower price. There is no competition on the resource. The grower is happy because they're going to sell trees at a higher price. It's a different market than wood chip. So that's a huge outcome for the project. And then when we manufacture the beam, we brought them back to Brisbane, and you can see that's how beautiful the beam is. This is manufactured from a tree that was going to be used to make paper. Yeah, that's crazy how beautiful the beam is. And that's another beam when testing in shear. We had a bit of issue with the manufacturing because the board was too thin. So the board unfortunately fell at the finger joint, but that can be fixed. But what we found, so we're not going to look at the bending MOR because failure was very premature to the finger jointing. But in terms of MOE, we can reach GL18. For the bending MOR was less because premature failures was only GL10, but the shear was good. And for the hybrid beam, in terms of MOE was GL13, GL10 in terms of bending, and we had the shear was GL8, but I think it's because we didn't have enough test results. But overall, if we're only looking at the MOE, it's stiff enough to make a commodity and high-performing product. We just need to figure out the finger joint and finger jointing. So glulam summary, the Southern Blue Gum, they're well suited to manufacture glulam. We can manufacture GL18 high-performing products, which is going to be typically going to houses to replace steel. It's a bit hard to glue, so manufacturer need to ensure that it's passing the Australian standards, especially for the high-density board. And at the thing, it's apparently they're going to be commercialized soon. So from the last I heard, maybe Gavin's got more news on that. So just I want to acknowledge the sorry, was I already got the conclusion for the LVL. I think I'm probably I'm on time, but the LVL for the LVL, it's we can't make visual appearance products, but we can make very high value LVL to commodity products. There is no technical challenge. It can be manufactured, it can be peeled, the recovery is well. It's performed as well or better than commercial LVL. So it's basically a no-brainer. We just need the facility in Australia to be able to manufacturing them. I did the conclusion for glulam. I will going to skip on that. I just want to thank everybody. It has been so helpful in the project. So the team at DAV, the Scott Wickers and Tim Wood was basically the team, and everybody at ABP Plantation, 141,